My name is Charlie Camarda. I work for the Office of Chief Engineer. I'm the Senior Advisor for Innovation. At the present time, at the time of the accident, when the accident happened, I was working in Russia. I was an astronaut assigned for a backup crew. And so we were training in Russia. It was in the evening. We heard about the tragedy.
Hello, I'm Stephen Scotti. I was the RCC Repair Deputy Project Manager during the post-Columbia return to flight effort. I also led the RCC research and development efforts, trying to look at a little more advanced approaches for repair to do larger area damage scenarios. The RCC leading edge of the shuttle is reinforced carbon-carbon. And during the Columbia accident investigation, it was determined as the root cause for the failure of and the loss of the Columbia, because damage incurred essentially led to the loss of the vehicle. So after the Columbia investigation, there was a large effort in looking at how would you repair the RCC leading edge on orbit if another damage occurred and a need arose. So the RCC project really resulted from that. It was led by NASA Johnson. The project, the RCC repair project overall, its goal initially was to repair a very large damage. That turned out to be a very difficult problem. So what happened was the project decided to, as a focus for return to flight, focus on the smaller damage efforts, so small cracks and small holes, and focus a lot of effort on that, but not to totally discount the large, possibly for large damage. They kind of gave that mission, that requirement to the RCC repair R&D effort that I was running. Langley Research Center got involved because we have a long heritage in high temperature materials and structures. A lot of work for the RCC leading edges development was actually done here at Langley. A lot of the early testing was done. We have a lot of expertise in the material system and in the structural mechanics that resulted in the development of leading edge. And also we have a large effort in damage tolerance and impact effects, so it was natural for us to be involved in the development of the repair activity. For the RCC repair effort, as I mentioned, we didn't know if it was going to be a requirement for the first flight post-Columbia. We worked as if it was, and the risk was that if we didn't have that capability, and we were not sure that the external tank, which led to the debris that caused the Columbia accident, would be fixed, so debris sources would be removed. We wanted a contingency repair capability. So the real risk was we're not sure we're going to be able to fix the debris problem that caused the damage on the Columbia. If we're not able to fix it totally, we want some capability to do on-orbit repair. And so that's what drove us to really push hard to develop a repair capability for STS-114, the first return-to-flight mission.
My area of expertise was in structures and materials, and especially high-temperature structures for hypersonic vehicles. I had done a lot of work on wing leading edges. And I went to my boss in the astronaut office and I said, I think I can help put together a team that can help the teams that are already in place at Johnson Space Center and industry at Thiokol, Boeing, and Lockheed, try to advance and accelerate their progress. I told them what I wanted to do. I wanted to put together this team. I was going to handpick people from around the country. We were going to go to Langley Research Center, use the navigation center there, to be off-site in one location where we could think outside the box, we could look at the problem, we could try to come up with some innovative solutions to the problem.
So we've been given authorization to work this RCC R&D effort for repair. One of the first things that I did was one of the astronauts at Johnson Space Center, Charlie Camarda, was someone I had worked with. He was actually my boss when he was here at Langley. So we decided to work together and put together a workshop to really beat the bushes, to look at all possible approaches that we could come up with to look at repair, inviting people from industry, from academia, from other NASA centers, cast a wider net than was done previously, and also make sure we're looking at all the requirements, which was not done as thoroughly as we thought in the past. For example, all the aerothermal heating requirements. We want to make sure we didn't choose an approach that would find out was not feasible because we forgot some requirement. So we had this very general focus workshop to look at that. We also had an EVA astronaut, Don Pettit, participating as well, and because he had the experience in terms of how to actually handle things on orbit in an EVA, which is a big part of installing a repair. So the workshop was held here at NASA Langley, a very large group actually, and we put together a very structured approach to look at the problem, discuss it, come up with options, and move forward.
What we did was, Steve Scotti and I grew up in a research culture. And so we worked in a branch, and I was the branch head of a branch that was very much a multidisciplinary branch. We had people within the branch that had skills in several different areas. So when we solved problems as almost like a little skunk works operation, the way we would handle it. Very tight budget. Go out there in a lab, do analysis, conduct tests, just like good engineers, correlate the analysis and test, and we would develop innovative ideas, different ways for solving problems. And it took that diverse group of people coming from many different backgrounds, including people that had expertise in manufacturing. We mapped out a program where we had the experts come and totally immerse the people in the problem, both the aerothermodynamics, the materials, the structures, what had been done before, what had been tested, and then we broke out. We taught them a little bit of the theory of inventive problem-solving trees. We had them all pre-read some material. I gave them copies of books, and then we brainstormed. We practiced brainstorming. I taught them different ways to evaluate their ideas and measure their ideas. The other thing that we brought to the table was we not only had people with a wide breadth of multiple different disciplines, we also had creative people that think outside the box that might not have been totally related to the problem. We also had experts that were down and in the world leading authorities in aerothermodynamics, for instance. So when people had questions, we can go directly to the experts and we can ask them a question. When you develop a team, if you want the team to be creative, you have to develop a culture, and that culture has to exist and flourish in the environment. The environment determines whether or not a culture of innovation can be sustained and will flourish. You have to allow failure. You have to recognize that everyone has good ideas, and you have to get them to work together as a viable team. And there are ways to do that. And creating that environment where it's okay to have silly ideas, where people can look foolish in public, and you're not required to know all the answers. Failure is important. It's critical for success.
So after the workshop, we had, as I mentioned, a large number of people with different backgrounds. And it started off with, after a little bit of education, what the requirements are. An aerodynamicist would talk about the aerothermal environment. A materials person would talk about material properties and characteristics. We had a huge brainstorming session, broken into small groups, mixing up the different abilities and experiences to make sure we had, a good cross-fertilization. And we literally came up with hundreds of possible options, truly brainstorming, not trying to synthesize or distill down to a fewer number of options. We cast a very broad net. We had a lot of options, literally hundreds, as I mentioned. And then we had to come up with some criteria as to how do you determine how to select some from the list of options. We created different teams that kind of worked with those buckets. So there was a team, for example, that looked at things that are based on metallic materials, things based on ceramic matrix composite materials, teams that looked at active systems or ablative systems, all different categories we had. And we put all this data into essentially large spreadsheets and organized it that way, and went back out to the group after the workshop. And for each of those approaches, essentially every member of the team that was in the workshop would comment on strengths and weaknesses. And doing that, that in combination with, again, some of the schedule pressure that we had from the project to say, okay, we've got to have things that we can do in a certain time frame. It actually was fairly easy to organize into a handful, let's say a half a dozen approaches that looked like they had all, enough figures of merit that looked good and also could meet some kind of real flight schedule. So that kind of organization really is what that evaluation led to, kind of an organization into sub-teams that focused on those half dozen or so areas that we thought had high promise.
When you come up with multiple ideas, you could have 60 ideas. You try to mature those ideas as far as you can in order to see if there's some potential there. And very early on, when you look at the ideas, you have to look at them very critically. You have to be very objective, even of your own ideas, and you have to be very critical. The minute you come up with an idea, just like any inventor, that idea is part of them. And they're going to defend that idea, and they can't see the faults in their own ideas. And so it's very critical for creative people to be able to look at their ideas and express and understand all the different ways that idea can fail. And so if you listen to Duke professor Henry Petrosky, who's written many books on failure, To Engineer is Human, for instance, and he talks about design being the process where you obviate failure. When you look at your design and you can come up and you could think about all the different ways it can fail, and you design out those ideas so that you obviate that failure, that's the whole beauty and the purpose of design. As
we got to a smaller number of options, we had to make sure we captured all the real requirements, including the installation of the repair, the manufacture of it, the qualification of it. So we actually did quite a bit of work, not just here at Langley, but at Johnson Space Center in the simulators to make sure that the approaches that we were having could be done by the astronauts. We were very closely tied to the EVA, the on-orbit work tools people, because they had to develop special tools for any installation, and that's their specialty. So we had a lot of interaction with them, folks in industry that actually were making the materials that we were involved and had selected as our smaller number of materials of the material set we were going to go forward with. We visited the factories. We had them on our team in our meetings. So it really has to be a very integrated effort. The first thing you needed was something that would actually withstand the environment, at least for 10, 20 minutes during the peak heating of the reentry. There's only a handful of refractory materials that can do that. One of the ones that are probably more applicable to the leading edge would have been ceramic composites. The issues of ceramic composites that people think, as they think of them, essentially they're rigid, stiff, and materials that break easily, fracture easily. So we had luckily had some activity at Langley looking at a solar shield that utilized a very thin, essentially a thin sheet of ceramic material, which we found was very flexible. And going through some of our development work there, we found if we tailored the fiber architecture such that it was very flexible one direction, very stiff the other direction, we could actually get a ceramic that was as flexible as a metal. And that allowed us to be able to take an uncertain environment, what's the shape of the leading edge, and rather than having a fit that only works for that one part of the leading edge and happen to have thousands of them essentially because the leading edge is complex contours, to have just a few sheets or a few designs of a flexible ceramic that could be used in lots of different locations. That concept was eventually adopted by the plug repair, which was on the main line products that was used in return to flight, and we used that for what we call our large area repair, which was to cover a very large hole on the leading edge. It was a flexible ceramic composite material system that we worked in-house and with some folks in industry to develop.
We had a prototype for a solution of the plug problem. Viacold's only solution was a very stiff 9-inch plug which was not flexible, and so because of that, it required 1,800 of these plugs in order to cover all the different surfaces of the wing leading edge. Our simple solution to that was take this brittle material called RCC and silicon carbide, carbon silicon carbide, and basically make it so that it's doubly curved. It's a doubly curved shallow shell, which when you press on it, it flexes and covers multiple surfaces. It snugs down nice and tight, and it maintains a very nice close fit so it doesn't disturb the airflow, doesn't cause any local heating, and doesn't burn up. Thiokol immediately saw that idea. We also showed them an idea for a step tap drill bit where we could drill and tap through carbon-carbon, and how easy it was to do that. And so Thiokol saw the idea for the flexible plug. They had an idea that they had been working on that they saw how easy that could be redesigned. And lo and behold, they redesigned their plug shape so that it was flexible and curved. And they reduced the number of plugs they would need from 1,800 to 18. And so we were able to carry 18 of those plugs on the first return to flight mission with the step tap drill bit so that in case we ever needed it, we could potentially repair the wing leading edge. So what we did was we designed a flexible plug. And when I flew up to Fort Worth, Texas, we kind of showed them the kinds of shape we were looking at. And we changed the shape many times. And this gentleman that I knew, Francis Schwinn, the same person that had come up with the idea for drilling and tapping the carbon-carbon to put a fastener in there, basically manufactured these for us. They prototyped them. They sent them directly to my house. And at that time, we were testing these prototypes using an acetylene torch, trying to represent the temperatures and the time at temperature to see how well they could protect, how well they would survive. And we took this fast failure approach, trying things, failing, learning, and improving the designs.
Also, it had to be such that it, when installed, it had a very small step up from the leading edge surface, because any large step would be heated, would burn through because of the aerothermal environment. Any kind of step like that would cause a heat spike and cause it to burn. Also, a sharp corner is also a bad for aerothermal heating, so you want it as rounded and smooth as possible. So that kind of those kind of constraints were our measures of goodness that really influenced the design of the plug repair and the other repair techniques that were developed in the project. Also, you needed a fastener that you could install that actually was compatible with leading edge, so we developed some ceramic composite fasteners that were machined, essentially looked like metal fasteners, only they're made out of ceramic composite. And those are part of the development effort as well. So taking all the pieces together, the drill, the fasteners, the cover material, the EVA tools required to handle all those on orbit, it's a system you're developing. It's not just a single entity. And having a team that looked at it from a system point of view was very important.
What we did was we went in the lab and we tried every way to design a drill to drill through carbon-carbon. And we tried things and we failed and we kept trying things. And many people said there was no way we could do that people had tried. They tried different torque settings. They tried diamond tip drills. What they didn't try was actually cracking the coating first. Using a spring-loaded center punch, chip the silicon carbide coating. And once that carbon-carbon was exposed beneath the coating, it was easy to drill through it. Very simple step to do. No one had ever thought about it.
A good example, I think, of actually covers two things. One, the diversity of team, and also giving an expert in an area enough rope that they can actually exercise some creativity, was the development of the RCC drill. We had a technician whose background essentially is tool making here at Langley. And essentially, we gave him the challenge, find a way to drill through RCC. Everyone that we talked to said that it just can't be done. There's no drill that can drill through that hard silicon carbide coating. So, essentially, here's a challenge. Go back and tell me how you might do it. And weekly we would check up on him. How are things going? We would interact with him. He would talk with some of the the astronauts about, what can you and cannot do in orbit in terms of how much force you can apply and things like that. And he quickly prototyped a couple different ways of doing it himself, because he was a tool maker. And then when he found some good approaches, he would demonstrate it for us. Come in and show us, here's using just things he could pull together himself, the ability to show that you can drill into a piece of RCC with a very low force level, which is what the EVA astronaut said was necessary. Otherwise, you're pushing yourself away from the vehicle. You really can't effectively drill on orbit unless your force impinging on it is very low. So he came up with a drill that actually pulls itself through. Essentially, it's a drill tap. It taps a hole. That tap pulls the drill into the material as it cuts the hole bigger. And it was actually eventually adopted as one of the tools for the plug repair, because if the plug hole that the plug repair was going to repair was not big enough, you want to be able to enlarge it and drill it out so you can put the plug repair in there effectively. So they actually, the drill tap that we developed for our repair capability became part of the mainline tool set.
What we would do is we would take the step tap drill bit. This is a crude mock-up of the drill bit, one of the first prototypes. This isn't one that we actually flew, but this was kind of the shape of it, and it was stepped so that the force that the astronaut used to begin to sink into the carbon-carbon and cut into the carbon-carbon wouldn't exert more than 5 pounds force over a very short length of time. Because if you did that, the astronaut in the foot restraints and the shuttle, which was connected to the space station by the robotic arm, would basically dynamically move away from each other. So it had to be critical. So the astronaut could potentially begin drilling, and once they started drilling, because it was cutting and tapping a hole, it would actually hold the astronaut there.
From the R&D perspective, one thing that we did learn was we could not make a decision too early in the process, because we would make a decision without enough information to really make a good decision. So we tried to keep as many options open as long as possible in order to do that, and then evaluate them truly through technical merit, not on just we'll choose this rather than that, without any real basis for making those decisions. So one of the lessons learned, I think, from the R&D effort is to keep your options open as long as possible in order to make sure that you're not throwing out a good solution without true justification. When you look at an effort like the RCC repair R&D effort from a systems approach, the true lesson, to my mind, is you have to have people with the expertise in a specific area working, but they have to be informed about the whole system. So they have to know what their little piece, how that interacts with the rest of the system. And so communication among the different disciplines, among the different subsystems and different focus areas was very important, but also giving people flexibility and ability to really kind of determine the direction. People say the failure is a bad thing. We've talked about that many times, and failure in this case is we try things and learn from it and then use that as a basis for making the next decision or making the next change in direction. One of the lessons that I take from the effort also is as we went and started really synthesizing the solutions from all the ideas, we had to very quickly screen through which ones would work and which ones would not. So what we try to do is very rapidly prototype the idea, use that prototype to answer the most critical questions that we thought, based on our experience, that needed to be answered. And if it didn't meet those criteria, either modify it or drop it. So essentially, you don't wait till you answer the critical questions to the end. You actually structure the project to answer the critical questions early on, make sure you have something that's feasible. Then you work to methodically mature it and make it more effective and a real product. One thing we look at in the research world is technology readiness level, TRL. One thing that we looked as a criteria is are there so many unknowns and things to be worked on that really it's not feasible to really get the idea to a point where actually it could be used practically in the limited time we thought we had for return to flight. So that became a filter through which some things essentially fell off the plate. You don't want to start from ground zero. You want to essentially not invent everything new, but take advantage of what's there now and adapt it as best as possible. A lot of things that we ended up with were adaptations of things that we were working on for other projects. I think one of the things that made our effort successful also is that we actually had support at the highest levels of the orbiter program. When we had, because we were looked on as something that they would really like to have at the very highest levels of the orbiter project as a contingency capability, we actually had the ear of the project manager. So periodically, we would actually go and give him briefings directly rather than going up through the chain of command and show him, essentially, here's examples. Here's a prototype of this capability or that capability. Hands-on. He could try drilling himself. He could try, installing one of our flexible repair materials himself. Just so it's not just a PowerPoint slide tool, but he actually could see this is real hardware. The most critical thing I think that should be taken as a lesson from this experience is that you cannot put boundaries up. You have to kind of keep your horizon as wide as possible. You want to don't turn away a good idea or exclude someone who has a contribution that they could potentially make, and also find people with passion. The people that contribute the most are ones that put a lot of, it's not just had good ideas, but put a lot of effort behind those ideas. They work day and night. I mentioned the drill, the RCC drill. Ron Penner developed that, and he worked weekends. He worked, refining it, making it work. It's like the Edison quote that invention is 1% inspiration, 99% perspiration. Putting that 99% in and putting that passion in there is important. So if you don't have that passion, you're not going to succeed. So getting good people with passion as well, so knowledgeable, passionate, and not excluding people that could contribute because of some artificial boundary that's created. So turn away no good idea, and if people want to help, give it a try. If they're not able to help, then you'll find out very quickly. But if they're able to help and given the freedom to do that, they will amaze you what they can contribute, especially if they're inspired. If you have any questions about the RC repair effort or research in general, especially on structures and materials, I welcome you to contact me at the Langley Research Center. I'm the Chief Engineer for Structures and Materials in the Research Directorate here, and we'll be happy to answer any questions you may have.